Hi, thank you for coming. I know there's a very exciting talk next door, so I really appreciate. What do you do when you're faced with a contradiction that your logical processes have brought you to? I think the sensible thing to do when you're faced with a contradiction, I mean, every theory that is naturally evolving is going to be faced with challenges. But after a certain point, when your paradoxes are starting to stack up, maybe your theory needs a revision, and it's time to check your premises. So you might want to take a trace back through the way you got to your conclusion and figure out where you made an error. You might find some kind of erroneous assumption or generalization, or maybe you made a misattribution of causality, and this is the point where you get to learn something. Of course, changing our assumptions is never very comfortable because they don't stand in isolation. The more you've thought about a particular belief, the more they are bound up with other assumptions that you have. And so then if you take back that assumption, you might have a terrible cascade that in the worst case could wipe out an entire worldview. And you can look at that as some kind of creative destruction like a fire, or it could be a threat to avoid at all costs. And then your strategy might be to ignore it or minimize it. And I'm as fallible as everybody else. So it's really important that we have a community like this with a lot of intelligent people with different assumptions, because it's a lot easier for me to explore what would happen if your assumption is wrong than it is to explore what would happen if my assumption is wrong, and vice versa. So we've got to help each other out. These graphics were distributed widely a few years ago. And they come from a study by Kara Ebling and others in association with the Boston Children's Hospital, which is associated with Harvard. It was from a study that was published in the American Journal of Medicine, and so it's a very prestigious group with clout, and what they say matters. And so apparently one of the things that they're saying is that low-carb diets and low-fat diets consist of things you can't eat, which makes compliance hard. The reason that they were studying these three diets is that they wanted to see their different effects on metabolic syndrome. And so they found that each of these diets had a substantially different effect on metabolic syndrome. And the low-carb diet clearly had the best results, but they didn't recommend the low-carb diet. They recommended the low-glycemic diet. I don't know, someone pointed out to me that traffic signals use red and green, which are 10% of males can't tell the difference between. But what we have is four green lights at the top. The low-fat diet has 3 red lights and an amber, and then low-carb has this mix, green, red, amber, amber. And so I was surprised at this. Why would they do this switch? And so stated so strongly. So I looked back at the paper and I was really distressed because it was hard to figure out how the translation between the data in the paper and the communications on the graphic could be so different without concluding some kind of systemic bias. I won't go into all the metrics, but for example, we've got a point here for hunger. Each of the different traffic light colors is represented, but when they measured subjective hunger in the different diets, they didn't vary with statistical significance. In the low carb in particular, they have this red light that has 2 parts. It says stress and inflammation. And the part that inflammation was based on was C-reactive protein. C-reactive protein was lower than baseline in all 3 diets. It was less lower in the low carb diet than it was in the low glycemic diet, but low glycemic gets green and low carb gets red. If they were going to be totally consistent, then since the low carb diet had the better effect on metabolic syndrome and the low glycemic was affected less, you might think they would at least get an amber for that point, but they don't, they get a green. So that's all very distressing. But The other point that's in red there for low-carb diet is stress. And you might think this is a plausible concern because that was based on measurements of urinary cortisol. And urinary cortisol is epidemiologically greatly associated with increased risk of heart attack. So I looked into, well, let's just look at what the press release says, first of all. So they said, this is how they stated this. The very low carbohydrate diet produced the greatest improvements in metabolism, by which they mean specifically markers of metabolic syndrome. But with an important caveat, this diet increased participants' cortisol levels, which can lead to insulin resistance and cardiovascular disease. So in other words, the low-carb diet had the best improvements in metabolic syndrome, but we're not going to recommend it because we think it might lead to metabolic syndrome. I just don't find this very persuasive. To me, it just looks like a contradiction. The markers that they were measuring for metabolic syndrome were triglycerides, HDL, and insulin sensitivity itself. And I agree that those are really good markers for measuring that. So what I did, like anybody else, is I looked for the assumption of mine that seemed to create the least damage if I took it down, and that was that cortisol has higher cortisol is actually damaging. So I decided to look at what the relationship is between metabolic syndrome and cortisol. I had already seen an argument about cortisol, which it was mistaken because it's based on this mistaken idea about blood sugar regulation. The idea seems to be that if you naturally let your blood sugar go low by not supplementing with exogenous sugar, then it's going to get so low that cortisol is going to have to come into play to bring you back into your normal range. And I'm not sure why people believe that because it's not how it works. I think it might be a mix-up with the direction of action. So yes, if you get a bolus of cortisol, that is going to upregulate gluconeogenesis. But that's not normally going to happen because long before cortisol kicks in, the dominance of glucagon is going to start to raise your blood sugar again. So glucagon's already taking care of the situation when you're down to about 65 milligrams per deciliter. And cortisol's not going to come into play until you're severely hypoglycemic, maybe at about 55 milligrams per deciliter. And I have heard of that situation happening maybe in well, if there's something wrong with your glucagon, or if you're doing very intense exercise so that your blood sugar is driven freakishly low. I've heard of that in some CrossFit situations. But it's not what's normally going to happen. And you'd know if it was, because the symptoms of that kind of hypoglycemia include tingling, blurry vision, faintness. It's really quite serious. And it's not what's going on a day-to-day basis in a low-carb dieter. So I looked at the paper to make sure they weren't making that mistake, and they weren't. There really were higher levels of urinary cortisol. And so I decided to look at what's going on in cortisol and metabolic syndrome. And that's a suitably complex topic, and this is only one little snapshot of it. I put a link to my website at the bottom because there are references for the different things I'll be talking about right now on my website there. But what I'm showing a picture of is basically we have cortisol and cortisone, which is the inactive form. They are converted back and forth by this enzyme at the top, 11 beta HSD. And the conversion from cortisone to cortisol is called the regeneration pathway. And then all these other metabolites that you're seeing come out of enzymes that are one-way functions. So if they go there, then they're destined for clearance. And you can measure these metabolites in different fluids like urine, blood, and saliva, and you can measure them at different times of day, and you can measure the enzymes themselves in tissue. But all of those measurements are trying to get at a proxy for what the processes are, of course. And it's the processes that are dysregulated in metabolic syndrome. It turns out that the pattern of dysregulation of cortisol in metabolic syndrome looks like this. Your regeneration gets lower, especially in the liver, and your clearance gets really high. So now you're stuck in a situation where your cortisol isn't high enough, and so your production has to go up to compensate for it. And often the production isn't good enough, so your cortisol will be slightly lower with metabolic syndrome. Funnily enough, in the Ebeling paper, they cited another paper by Stimson from 2007, where they were specifically looking at the metabolic effects of low-carb diets and low-fat diets in two groups of men. And they, by design, had both groups lose the same amount of weight, and then they were looking at what happened to cortisol metabolism. And this paper was cited because the end result of that paper was that there was a moderate rise in cortisol in the men on the low-carb diet, and that's indeed true. But the point of that paper was to show that it was only in the low-carb dieters that this specific pattern of cortisol dysregulation was reversed. So their regeneration in the liver went up, and their clearance went down, and their production also went down, and the end result was that there was a slightly higher circulating level of cortisol, and this was evidence that metabolic syndrome was being reversed. So whatever the epidemiology is saying, it's not the case that the higher level of cortisol that's being seen in the people in the low-carb diet is an indication of a progression of insulin resistance. It's quite the opposite. Well, suppose you were a scientist and you were working on an intervention that instead of it being something you weren't sure had benefit or not, it was something you knew had benefit. And so you put in this intervention, you saw the benefit, and then you wanted to take a bunch of measurements and find out what was behind this. And suppose you found moderately elevated cortisol levels in your subjects. What would you say in that situation? I think you would say, oh, well, maybe that's a mechanism of the benefit, because you already have that presumption. You already have the knowledge that it's beneficial. Well, this is exactly what happens in longevity research. Even short-term dietary restriction can attenuate inflammation and affect metabolic and DNA repair pathways. Mechanisms by which dietary restriction suppresses peripheral inflammation include the elevation of glucocorticoids. So, in other words, enhanced cortisol is part of the mechanism of benefit. And you wouldn't be alone in saying this. I chose only a couple. Here's another. Glucocorticoids are yet another class of hormones that may contribute to the anti-carcinogenic action of dietary restriction. Permit me one more. Another mechanism by which caloric restriction may selectively exert its anti-inflammatory effects is via enhanced, I like that biased word there, endogenous corticosteroid production. So it's considered a benefit to have elevated cortisol, just not to weight loss researchers. There are other similarities between ketogenic diets and the benefits that researchers are finding in the area of longevity induced by caloric restriction. So in both cases, we see an increase in the NAD plus to NADH ratio and an increase in mitochondrial biogenesis. We see a decrease in radical oxygen species, and those are all signs of metabolic efficiency. It's been proposed that the mechanisms by which those are similar is because of the ketone bodies themselves, and not just because of the fuel that they provide, but because of the signaling, which can affect brain-derived neurotrophic factor, nuclear factor kappa beta, and the inhibition of histone deacetylase, which has a proposed mechanism in mood stability as well as lifespan. The fact that there are these similarities, I think, is one of the main reasons that we have this analogy meme going around that ketogenic diets are mimicking starvation. And I think that idea is backwards for reasons I'll get into. Another reason potentially for why we associate ketogenic diets with starvation is because modern medicine was created after agriculture, where we were already having a high-carb diet. So when we first started looking at the effects of low-carb diets, we were able to recognize that there were similarities between what happens when people don't eat. But if we had been not on a high carbohydrate diet in the first place, that association would never have been made. But caloric restriction doesn't come without costs. In order to induce these effects in an animal in the longevity lab, you have to, but by definition, caloric restriction means you're not letting them eat what they would want to eat to hunger. And that means that they've evolved a signal to eat a certain amount. And and so it stands to reason that there is an adaptive advantage to eating that amount. And one of those advantages is the ability to reproduce. There's a prominent theory in longevity research that portrays longevity as a trade-off via caloric restriction with reproduction. And this was, I think, first discovered in worms, who have a very salient response to this. The idea, if I can anthropomorphize a bit, is that the body detects that there isn't very much nutrient and energy availability, and reproductive systems require a lot of energy and nutrients. So what they do is they say, well, I'm going to slow down living and just wait until I get a signal that there's food available. So there's a slowing down in the aging process, and there is much reduced reproductive ability. And the idea is that they're saving it up for more abundant times. Now, if ketogenic diets are mimicking starvation, then it seems to me that they are not going to be able to provide the prime of life vitality that we would seek. I don't want to eat a diet that makes me live longer, but I don't enjoy very much. I'm going to choose quality over quantity every time. Reproduction requires a lot of energy, and that reminds me of another trade-off. If you're not familiar with the expensive tissue hypothesis, then you should be next door in Nora Gagaudis' talk, where I think this is exactly what she's talking about. Basically, the idea is that at the same time as our brains were tripling in size, our intestines were drastically being reduced in size, and there is a proposed explanation for that. Since they're both very expensive tissues, we had to give up one in order to sustain the other. Whether or not that hypothesis is correct, the data stands that we did lose a lot of our intestinal tissue, and specifically we lost it from the cecum and the colon, which in other great apes is used to ferment fiber into fat, which they then use as energy. And so this loss rendered us almost completely dependent on external sources of fat. Most people believe that this had to have come from meat, fatty meat. I understand that in this community there's some discussion about whether that could have come from tubers. And certainly if we had the tubers available then that we did now, and the cooking that we had available now, that energy could have been provided that way. But that argument requires, it depends on an earlier advent of controlled fire than we probably had, or at least that so far we have evidence for. And then even if we had cooking, the tubers that were probably available at the time were not your modern white potato or sweet potato. They were very fibrous and couldn't have provided that kind of level of consistent energy, especially if you take into account seasonality. So what I would say is, yes, they probably contributed some energy inconsistently, but they didn't obviate the need for a very high-fat diet that was probably quite low in carbohydrate, at least for long periods. Our brains are very energy intensive. An adult brain uses about 20% of all the energy that we create. And this is even more prominent in children whose brains are obviously proportionally much larger and they're still growing. In other mammal species, brain growth usually stops either at birth or at weaning. Humans are different in that our brains continue to grow long past weaning, and even after the size has stabilized, they continue to have structural changes through adulthood. This picture stops at age 20, but structural changes continue for a few more years after that, at least. This requires a lot of energy, and it's a species difference. We have a parallel species difference, which is that in other species, most mammals, in the womb and during suckling, there are ketone bodies being used, not just to fuel the brain, but to structure it, the carbon backbones. I neglected to put my link on this slide, but it was my talk last year here where I went over a lot of the evidence for that, and you can find that on my website. In other species that do this, when the weaning stops, the brain growth stops, and the ketogenesis stops. In humans, brain growth continues, and ketogenesis continues insofar as children get into ketosis way more easily than adults do. Up to adulthood, it's basically an inverse relationship between ability to get into ketosis and age. And the tracking between brain growth and brain size and ketogenesis is so compelling that I almost want to call a ketogenic diet a brain growth mimicking diet. Next slide. I apologize, I meant to attribute this to Clark and Kubrick, and if you don't get the joke, I'm sorry. Even adults, though, are very, very easy to get into ketosis compared to other species. We have this unique ability to be completely calorie sufficient and completely protein sufficient, and as long as we're restricting carbs, we're going to be in ketosis. I don't know any other species that does this to the extent that we do. Rodents come the closest that I know of. So Dr. Finney's group was able to get mice ketogenic at some kind of ad libitum diet that was mixed, very high in fat. But he told me that the line between adequate protein and too much protein for ketogenesis is vanishingly small. Similarly, I spoke with Ben Beekman, who was working with rats, and he said it took his group a very long time to get the rats to be ketogenic without restricting calories. It was very frustrating. When they finally had accomplished that, it was a 90% fat diet, and then we have to start talking about definitions of ketosis, because the level that those rats were getting, I may misquote, but I think he said it was a quarter more than the control group, whereas in humans it's tens of times. The difference is really extraordinary. You might think that carnivores would be ketogenic because they don't eat any carbs, but in fact that's not true at all. As long as there's adequate protein, they don't go into ketogenesis. They don't do that until there is inadequate protein. I would love to see studies in other great apes. I was unable to find any. If you know of any, please let me know. My suspicion, my hypothesis would be that they would not have the ability that we have just because of that relationship to brain size. Our brains are about 3 times the size relatively to other primates, to other great apes. And another data point that makes us special is our fat level. Other great apes, a lean human has about 3 times the amount of body fat that you would expect in a primate, given our other relatives. And Stephen Cunnane and others have proposed that the reason for that is to be able to supply ketones for the brain. This is really a special ability. And I think that if we were making this adaptation, or in order to provide energy to the brain, then, and we made it to such an extent that we could have full calories and full protein, I can see that yes, the more protein you eat, the more ketogenesis is going to go down. But I don't think these studies have been done under full calorie sufficient conditions to compare different levels of proteins, but anecdotes suggest that the tolerance, the margin that we have for that is, for many people, you could eat 1.5 to 2.5 times your minimal protein needs and still be in mild ketosis. So we are able to do that, and that means we are able to be ketogenic without threatening our survival and with during periods of intense growth. So the idea that being ketogenic in a human is disruptive of hormones in the same way that starvation would be seems like it might be misguided. If you view ketosis as a clever hack that can be used to treat certain diseases, but that it's not sustainable because it's basically emulating a starvation mechanism, then you're going to have a very different interpretation of the observations that you see than if you believe that ketogenesis is something we evolved to support our brains and to support our reproduction. If you aren't really convinced that a low-carb diet is good for health, then as soon as you notice something unusual, you're going to worry that something's wrong with the diet. This is Goodhart's law. His idea is that if you have a measurement that is a loose proxy for something that you really care about, but that measurement's way easier to measure and quantify, and then as a society or a group, you start targeting the measurement instead of the thing that you really care about, then that correspondence begins to break down. So examples of this might be standardized tests where it originally was designed to measure some sort of competence, but then the teachers start teaching to the test and the correlation breaks down. Or you might say that using statins to address LDL are not going to have a big effect on heart disease because the correspondence between LDL and heart disease is not ever really causal in the first place, and so it's not going to have an effect. The kind of worst perverse example or paradigm that I see as a kind of reverse view of Goodhart's law is medicine that's addressing symptoms and not causes. So if an athlete is injured and you give her a painkiller and send her back out on the field, the absence of pain is no longer a good indicator that she's safe. What we really want with symptoms is to discover what the underlying cause is so we can address that. But that's a really hard thing to do. The diagnosis is an art, and in part because we don't know what causes everything. And sometimes there are multiple things that can cause a set of symptoms. So at that stage, one way that we cope with that is to take measurements of different biomarkers that might have correspondences to sets of symptoms that might help us distinguish what the causes are. So here's an example of a set of symptoms, and there are many causes for these symptoms, and when they come together in a cluster, they're very often associated with hypothyroid. But hypothyroid itself has many different causes because there's so many inputs to the system. It's part of your metabolism. So if you present these symptoms, the next step would be to get a panel of biomarkers like this, and see which pattern it might correlate to. Here's a pattern that you don't normally see on a high-carb diet, but it's routinely seen on a low-carb diet. And when it's on a low-carb diet, it's asymptomatic. And usually, generally, the lower the carbohydrate, the lower the T3. But the only thing that's really abnormal about this pattern is that the T3 is lower than the reference range that was established on a high-carb diet. But why would you expect a metabolic parameter that is at one level when you're making ATP in one way to be the same as it would be when you're making ATP in another way? The same argument can be made for vitamins. Vitamins are basically enzymes that are required in metabolic pathways. And if you're comparing the enzymes that you need to metabolize glucose in the cell versus ketones and fat, you should expect very different reference ranges. And I would submit that most of our RDAs are completely useless once you're talking about a ketogenic diet. And I would say the same thing for T3. This pattern has been studied before because it does occur sometimes in high-carb diets. And when it occurs there, it's because of either a critical illness like sepsis or in protein or calorie restriction. And if you wanted to know if this was a side effect that's damaging versus a helpful adaptation, one way you could distinguish that is if you supplemented with T3. Unfortunately, when they've done this in critical illness, the results are mixed and we still can't tell. But when you do it with calorie or protein restriction, the difference is that if you supplement T3, you will lose lean muscle mass. And so it seems that the function of T3 here is to preserve lean muscle so that you don't end up with a situation like this where you have a low-calorie, high-carb diet and you're suppressing that lowering of T3 that might help you preserve your muscles. What if you are having the symptoms of hypothyroid and you are on a low-carb diet? So you could go through this red herring process of discovering that your T3 is low and thinking that that's abnormal, even though that's just a feature of ketosis. But with all due respect, I think that what might be going on is something more like this. You know that a low-carb diet might help you lose weight, but you've also been getting mixed messages of the form of that Boston Children's Hospital where you already believe meat's bad for you, fat's bad for you, there's nothing left to eat but salad. Or you might have bought into the high-fat part of the high-fat, low-carb diet, but you're so concerned with your measurements of ketosis that you've brought your protein levels down to just the bare minimum or even lower. This is conjecture of my own, but it seems to me that a lot of the symptoms that are characteristic of hypothyroid might just be symptoms of not eating enough. How much serum ketones do we need? This is a personal measurement of mine of 0.9. I often see that, or even lower, and I think that's just fine on in a weight-stable situation. But if you really want deeper ketosis, the easiest way to achieve that is to just get rid of more carbohydrate. Because if I know that I can be ketogenic on a diet and containing 20 grams of carbohydrate, and I get rid of those 20 grams, I can add 40 more grams of protein before I even have the material available to create as much glucose. This is Andrew Scarborough, and he cares a lot about the actual ketosis level, unlike me, because he's using a ketogenic diet to keep his brain cancer in remission. And so when I first heard about him, he was doing this ketogenic diet, but he felt terrible all the time. He felt tired and weak. He gave up all his carbohydrates and was able to raise protein for the same ketosis level, and he feels great now. So it's definitely worth looking into. I just want to finally leave you with these sentiments. This is from a recent a commentary on a paper about cancer, using ketogenic diets for cancer, and the problems that seem to be coming up, one of which is a lot of side effects. And this research group is out of Hungary, and they're using what they call a Paleolithic ketogenic diet, which is essentially just meat and fat. They will sometimes add very few other things. And what they say is, we view ketosis as a physiological rather than a pathological condition. It follows on from this that the negative effects of the classical ketogenic diet, which, by the way, they're not seeing, do not result from the ketosis itself, but as detailed above, emerge from an unhealthy and evolutionarily maladapted composition of these diets. So in other words, what they're saying is, if you make a ketogenic diet because it's based in meat and fat, which is a match to our evolutionary heritage, that's one thing. But if you take Neolithic foods and then mess around with the macronutrients to try to get ketosis, what you're creating is a pale imitation of the diet that should support our health. So because we developed this special ability for ketosis, I don't buy into the narrative that starvation is what we are emulating here. I think what we're emulating is the ability to support our immense, unique brains under full nutrition and calories, and that to worry about hormonal effects is to presuppose that ketogenic diets are not natural. And even if you believe that we had some carbohydrate in our ancestral diet, I think that most people would agree that we at least had long periods of at least mild ketosis, and that this is a natural state for humans.
Thanks. We've got about 4 minutes for questions, so I don't know if there's there's no microphone over there, so maybe just shout them. Yeah, either go to the microphone or shout it out, and we'll repeat it.
Hi, I'm just going to read something I found real quick. The Boston Children's Hospital has this low glycemic diet program, so that might explain why they preferred the low glycemic diet in the study, even though carbohydrate diet was beneficial in a lot of ways. But my question is, how long does it take for the glucocorticoid? Do they stay elevated forever? And is that associated with any negative health consequences, or is it just a short-term thing? One question I haven't seen answered yet is, how long can someone on a ketogenic diet stay healthy and stress-free and have a healthy thyroid?
Right, so that's a great question. One thing that I didn't talk about was the degree of elevation of cortisol. So we hear a lot in the media of the harmful effects of long-term exposure to cortisol in the body, and that might make us worry even if we're okay with the idea that it's coming about in a natural way. But just to put a finer point on it, the symptoms of prolonged exposure to excess cortisol are abdominal obesity, puffy face, fat around the neck, and fatigue and high blood pressure. And so far, I've never heard of those symptoms in long-term ketogenic dieters. We don't have modern studies of long-term ketogenic dieters, unfortunately. We can maybe speculate that if you believe that in our evolutionary past we were ketogenic for the long term, as I'm trying to promote that idea here, then you would say, well, we've done that trial. But unfortunately, I don't think we've done that in any kind of controlled way in the modern times.
Thank you so much for this really fascinating view of keto, especially that T3 piece. My question is, in the rule of thumb of thinking of short-chain fatty acids in the gut biome, how does this perspective relate to that in terms of supporting that healthy microbiome and sufficient short-chain fatty acids that would come from unfermented fibers in that gut biome? And then in addition to that, sort of out from that, what would there be any kind of dietary nutrients that would be missing, and how would you obtain those in a longer-term version of what you are outlining here.
Okay, so how much fat can you get as a human from fiber if you were to eat the max, whether you're on a ketogenic diet or not? I think is really quite low. I've done some back of the envelope calculations. A gram of fiber can get you about 2 calories, but we can really only process maybe 20 or 35 grams a day without experiencing gastrointestinal distress. So that, I think, would be under 5% of your stereotypical 2,000 calorie a day diet. And getting that in fiber, regardless of, you may or may not know what I eat, which is a plant-free diet, but regardless of whether you eat some plants that are fibrous, that doesn't necessarily interfere with your ability to be in ketosis. So you could definitely eat a diet that contains a lot of low-starch plants and still be in ketosis, and that may or may not address the question that you have about feeding the microbiome. As to nutrients, meat is quite nutrient sufficient, and not only is it a better source of all the nutrients that the brain is really dependent on, but it can provide all the nutrients that we need.
I'm actually more interested in the short-chain fatty acid question from the standpoint of the plant-free diet. That's what I'm really curious about, the how, the sustained health of the gut biome. I think that's really
Right.
Compelling idea, and I wonder if you've come up with some information about that.
Sure. Well, I have many different answers to that question. One of them is that if you look at germ-free mice, they certainly live longer and are healthier than the wild strains, and so whatever the effect is on the gut microbiome, it's not enough to make them unhealthy. But you could also point out that many of the functions of butyrate, for example, can be replicated by beta-hydroxybutyrate. But moreover, you can make butyrate with bacterial strains that are working on amino acids. So it's not like if you didn't eat plants, you wouldn't have any butyrate. But that's a really great question, and I would love to talk about it longer.
So I was very interested in your citation of Goodhart's law, and also the idea that a reference range established for one physiological state or diet might be not relevant for another one. So your example of T3 was eye-opening. What would you say about vitamin D? When I went ketogenic, it dropped, but I don't have any of the symptoms that people claim are associated with lower vitamin D. So could that be more of a consequence than a cause of certain conditions? Have you looked into that?
Wow, I've never looked into vitamin D in particular. The only things that I've read about vitamin D are that it's hard to know if vitamin D is being, insofar as there are correlations between low vitamin D and disease states, we don't know if the disease is being caused because the vitamin D is not high enough to support some function that we wanted, or if some people have proposed that vitamin D has an immune function, and when you're sick, it gets used up a lot faster, and that's the source of it. But I really don't know. I will have to look into that one.
And the second question is, I was intrigued that you see ketosis as supportive of brain growth even in childhood and infancy. Are you aware of modern humans who raise their kids ketogenic, and are there any issues seen with growth of the brain or any abnormalities, or is it a perfectly sane way to raise children?
Only on a anecdotal basis, but if you look at my AHS talk from last year, it's called optimal weaning from an evolutionary perspective.